In the second part of this lecture, we'll examine the concept of a hazard in the pipeline. So what is a hazard? A hazard is a word in English that comes from the French word hazard, and this was the name of a game. That's the origin of the word. And this game is a game of chance played with a dice. So the idea of a hazard is that unexpected things can happen, and is in that concept that the word hazard is used in computer architecture. So what are the hazards that we need to be concerned about? There may be situations that will prevent the starting of the execution of the next instruction in the next cycle. And these situations may happen for different reasons. There are three different reasons where this could happen. The first is called a structural hazard. A structural hazard is when a resource is needed, but the resource is busy at that point. The processor cannot start the execution of the instruction because it doesn't have the resource. The second hazard is that the instruction may depend on data that was produced by a previous instruction. For example, if I have something like this, where I have a load instruction that produces the value of t0, and subsequent I have an add instruction that uses the value of t0, the value of t0 may not be ready for the add instruction to use at the time that the add needs it, and we're going to look in the next few lectures about how we fix that. And the third type of hazard is what we know as control hazard. A control hazard happens when you have a conditional expression that will decide which is the next instruction to be executed. Remember that I need to be constantly fetching instructions, and until I have a decision here that I know what's the result of the condition of the branch, I will not gonna know whether I need to fetch the add or fetch the shift right logic instruction. So let's start talking about structural hazard. So one of the things that we have told you up to now is that the processor needs two memories, a data memory and an instruction memory. This is one of those small lies that we have to tell in computer architecture until we can expand the design. And as you know, no processor has two memories. Processors only have a single memory, and we have been discussing from the beginning of the term that we fetch instructions and we fetch data from the same memory. In all your assembly programming, you have the data area and the text area for your programs, and they both go into the same memory. So how do we solve this problem? So first of all, we need to know that there are no two memories, so there is only one memory. Therefore, the instruction fetching that we send the PC to that single memory, and the result from that memory that comes when I fetch an instruction is the instruction that's used. So that's the fix that I had to do to my design to make it more realistic. So now I have a structural hazard. The structural hazard happens because the data access that I need for the load and store instruction, I need to fetch an instruction and I need to access the memory at the same time. One for a load or store instruction that I'm executing, and the other is the fetch for another instruction that's coming in the future. So how do I solve this problem? So if I have a pipeline design, I must have instruction and data memory to be separate. But as I said, we only have a single memory in the machine. So what happens is that all modern processors will have a separate instruction cache and data cache. I know we haven't studied caches yet. We're going to study caches in the next couple of weeks. But the important concept here is that there is this cache memory that is at a higher level of the memory, and the cache memory is separate. And that's how I resolve this structural hazard. Let's discuss data hazards. A data hazard happens when I have an instruction that depends on the result or the completion of the data access by a previous instruction. So one example is that I have an add that produces the value of x1, and then I have a sub instruction that consumes the value of x1. So this is what we call a data dependence, and this is called a true data dependence because I have to actually obtain the value of x1 in order to compute the sub. So if I look in my pipeline, this will be the execution of my add instruction, and this is time going in this direction. So this will be after 200 picoseconds have passed, after 400 picoseconds have passed, 600, 800, and 1000. So at the end of 1000 picoseconds, my add instruction is completed. But look at that, my sub instruction comes immediately after my add instruction. The data will be available from my add instruction at this, this point in time here. And my sub instruction that will need that value will not going to be able to start at the time that it was supposed to start, because if I start my sub instruction here, what's going to happen is that it needs the value at this point, and the value is not available. So in order to solve this, what I need to do is to delay the execution of the sub instruction by 2 cycles in this case, so that I can line up the instruction decoding cycle of my sub instruction with the write back cycle of my add instruction. I assume that I can write to a register and read from the same register in the same cycle in my design of the register file. So if I line those things up, what's going to happen is that the value that I wrote in the add instruction here, the value of x1, can be read in the sub instruction. So what happens in the 2 cycles in between? This is what we call a bubble. We have insert a bubble in the pipelining so that we are delaying. So this is the equivalent, if you think of the pipeline being an assembly line, there will be 2 stages where nothing is being produced because there was a problem in the assembly line. And this is what a bubble in the pipeline means. So we would like to not have such bubbles because they decrease our performance, and we need to look into solutions that we can have to avoid such bubbles. So one solution is to use the result not when it becomes available in the register file, but when it's computed. So I do not want to wait for the result of that add to go all the way to the register. I want to use it at the moment that's produced. To do that, I need to have additional connections in my data path, and we're going to examine these connections in more details in a future lecture. But I'm going to have additional connections in the data path that will going to enable me to do what I call a bypassing or forwarding. I'll take the value from the output of the execution unit for the add, and I'll send that value to the input of the execution unit for the sub. Remember that those two are the same execution unit, so I taking the result from the output of the arithmetic and logic unit and bring it back to the input of the arithmetic and logic unit without going through the register file. This is what we call a bypass or forwarding in the pipeline, and it enables me to have a more effective pipeline. The other type of hazard that we need to look into is the load use data hazard. So a load use data hazard happens because the result from the load instruction is only available at the end of the memory stage, and if I have an instruction that immediately follows the load that's using the value of the load, that instruction will need that value at the input of the execution stage. So the data is available at this point, and the data is needed at that point, and I need to do this forwarding. But I cannot do this forwarding by putting the 2 instructions one next to the other. In this case, I do require a bubble. I have to have one idle cycle in between, because if I try to put the sub right where this bubble is, what's going to happen? This will be the decode of the sub. This will be the fetch of the sub, this will be the decode of the sub, the execution of the sub will be here. The data would be needed at this point, but it's not available. So the data would be needed at the 600, but it's not available until the 800. This is not something that I can avoid with forwarding. In the previous case, I could avoid all the bubbles, so I could put one instruction immediately after the other by having this additional path to send the data, but in this case I cannot, because the variable is not available when it's needed. I cannot send the value backward in time, right? So if I try to do a forward from here to here, this would be sending the value back in time, and that's not possible. So here's an example of code schedule to avoid stalls. So the problem that we want to solve here is to generate assembly for this C statement. So A is equal B plus E and C equal B plus F. And this has to be translated into load the value of B from memory, load the value of E from memory, compute the value of B plus E, and then store the value of A into the memory. For the second instruction, I already have the value of B that I loaded previously from the memory, so I just need to load the value of F, compute the value of B plus F, and then store the value of C. So this gets translated into two loads, an add, a store, a load, an add, and a store. And if I schedule the instruction in this fashion, what is going to happen is that starting at the time 1, I can execute this load instruction, and I assume that I have the value of T0 already computed before, so I can proceed without stops. The second load also can proceed without any delay because it has the value of T0. But when I start executing my add now, I can do the instruction fetch, I can do the decode, but I cannot execute this instruction because if I look at the values that this instruction needs, it needs the value of T1 and T2. The value of T2 is only available after the memory stage of the load instruction, the second load instruction has computed. Therefore, there will be a delay of 1 cycle here where the add has to wait because there is a data hazard. Next, to execute the store instruction, I can do the fetch, I can do the decode, and the store instruction needs the value of T3 to store, which will not going to be available until the end of the stage the time 6. So the store also get delayed by 1 cycle. Next, I need to do a load. And the reason the load has to skip this cycle here is because it is a structural hazard. It's not because of data dependence. I'm assuming that the value of T0 has been known since the beginning, but I cannot have 2 instructions executing using the execution unit at the same time. I cannot have 2 instructions using the arithmetic and logic unit. So this delay here is different than that delay because this delay is a structural hazard delay. Next, when I try to execute my add now, and sorry, there is a dollar here. This dollar needs to be removed. It's a typo. When I execute my add now, what will going to happen is that the add depends on the value of this load. Therefore, I have an additional delay here because the value of T4 is only available at the end of the memory stage of the load, and only at that time I can proceed with the execution of the add. And finally, I do my store, and the reason the store is going to have to wait the cycles is because the store has to wait until after the add has finished using the execution unit. So this is the code that I generated initially, and what actually happens is that I keep fetching again the instruction, so I don't have these gaps in the pipeline. What happens is that I delay at the instruction fetch stage. So this took 13 cycles to execute. Now what I'm going to do, my compiler is smart, and my compiler understands how the pipeline works and understands that I should not be using the value of a register immediately after I load, because that causes these delays in the pipeline. So my compiler got smart enough to figure out that I can perform my loads first and then perform the other instructions later. So this is called instruction scheduling. Instruction scheduling is the problem of deciding the order in which your instructions are executed. So when the compilers generate an instruction scheduling, the only constraint that the compiler has is that it must follow all the data dependencies in the program. But as long as it follows the data dependencies in the program, it can reorder the execution of the instructions. So with the reordering of the execution of the instructions, let's see what happens now. Again, just like before, my load can proceed without delays. The second load can also proceed without delays because I have the value of T0 and there is no structural hazard. The third one can proceed as well. Now let's look at what happened with this add here. This add needs the value of T2, which is computed by this load, and the value of T1, which is computed, obtained by this load. So if I start the execution of this add at this point, when I get to the execution stage of this add, I already have from the memory stage of that load the value of T2, so I can forward that value to the execution unit. And the value of T1 is already in T1 because the write back of the load instruction has already occurred. So it's a single forward here from the memory to the execution unit. I can proceed without delays. I need to compute my store. There is no structural hazards for my store now because when it needs to do the execution stage, the execution stage of the add has already finished. And now for my next add, again, it needs the value of T4 and T1. T4 is already into the register and T1 is also already into the register. The write back of this first load in this third load has already completed. And finally, I can do my store without any hazard, and I managed to complete the execution in 11 cycles. So at this point, I expect that most of you have already understood what's going on here, but for people that are more visual learners, I have created a pipeline for you to see exactly how these delays occur. So in the original scheduling, where I had not reordered the instruction, my compiler had not done its job, what was happening is this. In the first unit, the first instant of time, I fetch the first load instruction into the first stage of my pipeline. And I like this graphic representation here because this makes clear that there is only one instruction fetch stage, there is only one instruction decode stage, etc. It's not like each instruction has its own. So in the second unit of time, what happens is that the first instruction, that first load moves to the decode stage, and the second load moves into the instruction fetch stage. In the next unit of time, my load moves into the execution stage, my second load moves to the decode stage, and my add moves in the instruction fetch stage. And now what is supposed to happen is that my load move into memory, my execution move into memory, and I find out that I need a bubble in the pipeline in the sense that I'm not going to be able to proceed at the speed that I had before because I have this data dependence between the load and the add. So what happens here is that that instruction that I had fetched earlier, the first time that I fetched that first add, will be converted into a no-op. A no-op is an instruction that has no effect in the state of the program, and the instruction fetch will be fetched again. So if I rerun the animation, what happens at this point, I already have the add in the instruction fetch. I detected that there is a hazard that I cannot fix with forwarding. I insert my bubble here, that's my no-op, and I fetch my load, my add instruction again. So summarizing the big picture for this lecture is that stalls will reduce performance, but they are needed to produce correct results. The compiler can rearrange the code, we call that instruction scheduling, to avoid hazards and preventing stalls. But in order to do that, the compiler needs to know about the pipeline structure. So one of the motivations that we had in the first lecture of this course as to why computing scientists need to understand about assembly instructions is because compilers are designed and constructed by computing scientists. And when we say that the compiler requires knowledge of the pipeline structure, it means that the compiler designer needs to understand the computer architecture and understand how the instructions flow through the pipeline in order to generate an instruction schedule that produces good performance. So that's what I had for our introduction to pipeline lecture.